Before we get into today's material, I'm just going to step back and go over what we did on Monday. Obviously, we missed lab yesterday. I'll be posting a little video on what I was going to have you guys do in lab. There will be another lab assignment posted. It's going to be almost identical to the last lab you guys did. It's just going to be changing some VLSM stuff around. The idea that we're trying to drive out to you for labs is to be comfortable with setting up address blocks, how to assign them, and assign the correct ones. They get a little anal to tell you what numbers to be putting at certain locations. Follow directions. Obviously, if you have a whole range of them, it wouldn't matter if you get any number in there in the real world. But for Packet Tracer to able to assess your ability, it's going to be this address for this device and that address for that device. I'm sure you saw that in the last lab. On Monday, we got into the data link layer, and we were talking about logical topologies versus physical topologies. And basically, the three logical topologies I got into, I believe I only did two, was the ring topology, the multi-access, which I called the bus, and then the topology I'm going to get into today is going to be point-to-point. Yeah, well, and that's where I'm going to get into this with point-to-point, because I did mention something about star topologies, and I said, well, that's multi-access, but it's with a little flavor, because you can get really carried away with logical topology, especially when you start getting into hybrids, when you take multiple topologies and join them together to get the benefit. The idea of topologies is they're giving you the concept of how the data signals will behave as they travel on a higher level. They're not telling you how to physically lay them out and map them together. So I simply drew a circle, and I called that the ring topology, right? That's the way it would look like on a sheet of paper. That's the way I'm going to draw it, because to me, logically, it tells me that data is going to flow from this device to this device to that device. By the way, the letter N is short for node, right? We're not saying network. And we're just going to keep on going around in circles like this. Why would we implement this technique? For the same reason, why do we implement roundabouts when it comes to our highway infrastructure? So why this? Logically, what does this give me? And what is the whole purpose of the data link layer? What's this? Yeah, it controls the flow of data. I mean, the whole purpose of the data link layer is to put frames on the medium and to take them off. Well, sometimes the medium is going to be shared. Look at this situation. The medium is shared. This is the common medium. And remember the definition of a network. Two or more devices connected together over a common medium governed by the same set of rules. We clear about that? So if these are connected together through a common medium, there's going to be a chance of collisions. When it comes to ring topology, we eliminate that. How do we eliminate that? By using a controlling method, which I told you is going to be called deterministic. We're going to control this. We're going to say, okay, for the person who has the token, you're allowed to talk. Only one device on this topology or network is allowed to talk. If you have the microphone, say what you want to say, then let everybody else respond, if you will. This eliminates collisions, but what does it cause? Additional overhead. Because we got to deal with timing and who has what. Now, performance is always questionable, because if you have a lot of users on this network, then what's going to happen to collisions? Well, collisions don't exist, but performance, would it go up or down if you increase the number of users? Interesting. We'll come back to that at the end of class, but I just want to let you guys know that we typically use these ring topologies when we connect cities together. Okay? Locally, we move away from ring topologies and we create what we call multi-access. It gets its name because this common medium this backbone, if you will, is accessed by more than one device, correct? Okay. Collisions can occur. In fact, this typical topology is implemented locally, like in a network like this. Why would this topology be implemented on a network like this versus this typical topology? And by the way, when you look at a network like the way I'm looking at this network, do not think that in a ring network you must arrange your desks around in a circle like they do in English class. What's that? Typically, the physical diagram for a ring topology might look something like this. 3 nodes, or even 4, doesn't bother me. It just goes on and on. This is connected to that one. This is connected to that one. That one's connected to that one. And then the end, or the last node, is then connected back to the first node, correct? So you guys really have no way of looking at something physically and determining the logical topology. When you look at the logic topology, you're thinking how it behaves. All these devices in this classroom come to one central device. You might not know what that central device is. And that central device, that intermediary device, is going to dictate the logical behavior. If that central device was a hub, then the behavior that it's going to dictate is going to be something like this. And that is when somebody puts a frame on the medium, all the other devices are going to get that, right? So in this bus topology, we need to concern ourselves with collisions. We need to develop a mechanism that can detect collisions and recover from them. So what are we going to do? If this node wants to communicate with that node, remember that any node that's connected to that medium, that common medium, they're all going to get it, correct? And so I said that the data link layer had to handle some addressing. And remember the 2 sublayers of the data link layer? The logical link control, which is going to do all the orchestrating between the software and the physical layer. It's going to do the framing, if you will. And then the MAC layer, the media access control, is going to be responsible for telling the physical layer what bits to put on the medium, and also detecting the framing address, the media access control addressing. I don't care what type of topology we are driving to, we need to try to get to the point that we understand that each of these devices are going to have a local address, a physical address that when they're connected to a common medium will help them determine whether or not that frame is destined for them. And remember, a frame is a PDU for the data link layer, correct? Just like a packet is a PDU for the network layer. So when I look at this, each of these devices are going to have some kind of physical address. If I'm using a hub, in this case I'm representing that, when the frame gets put on the medium, it's going to be shared through all the other devices. These ends are called the terminators, and that means the signal is going to stop its propagation. Okay? Now we could hook this up to a router and it would stop its propagation at the router, because what does a router do? Breaks the network up into broadcast domains, correct? So here we are, putting a message on there. Node 1 wants to talk to node 3. Node 2 is also going to receive that. But the question might come up is, what happens if node 1 and node 2 both want to talk to node 3? In a ring topology, it's controlled. It's deterministic. I know the data is flowing in one direction. That means as this gets passed through there, this computer is going to check that token, if you will, the carrier, and say, hey, if there's nothing on it, let me put something on it. Okay? It's no different if I pass around a cart, and if you see something empty, just add to it. If it's full, just keep on passing it around. And if your name's on that package in the cart, you're going to take it off, correct? And then you're going to pass it. Next person sees it's empty, and if they have something to put in there, they're going to do that. No collisions. Here, we're dealing with a non-deterministic method. Why do we call it non-deterministic? There's no control. Why isn't there any control? Can you guys control the electricity that flows from one outlet to another if they're both part of the same string of outlets? So for instance, if you plug in a device right here in this outlet and then plug in another device into this outlet up here, the electricity that's flowing from those outlets all the way down through is the same electricity, correct? So there's really no ability to determine what devices are allowed to have access to electricity when they're all plugged into the same circuit. Does that make sense? This is really critical here. When I want to deliver a message to another device, I need to use electricity. That's my carrier. If I'm using copper wires and all these copper wires are touching each other, when I put electricity on one copper wire, what's going to happen to all the other copper wires? They're going to come alive. They're going to receive the voltage, correct? Voltage will represent our bits. Hence, I have no way of controlling that. So what am I going to do? Why would I implement something like this when I have no control over collisions? Who's talking when? Like over here, I do have control. I hook up a wire from here to here. That'll stop the circuit. That'll stop the electricity. Then I'll hook it from here to there, and I'll continue doing this. All right, folks, I have been really good this semester about laying down on you. This is your time that you pay for me. If you are doing anything other than paying attention to what I have going up here, then I'm going to ask you to leave. You're disrupting other students. I'm not going to single anybody out, but this is your only chance, your last warning. I warned you at the beginning of the semester. I'm being very delicate, okay? So, from here on out, if I start seeing other things happening, and by the way, the camera is running and I do notice this, I do not feel like being a parent. I don't have any kids. I don't want you guys to be my kids. You are my students. I am your instructor. Let me do my job as teaching and don't make me a disciplinary figure, okay? Because it's real simple. The door's there. If I am boring you, you do not need to be here. If you find this stuff below you, if you will, fine, engage me. If you're not catching it, ask questions, okay? I know for most of you this is not your major, and I'm fine with that. Indulge me. Only asking 55 minutes of your life. The class will go a lot better if those 55 minutes are spent with you being engaged, enjoying by actively learning. Raise your hands, engage. You'll have a better experience with all this. Okay, guys? Let's get back to this. Here we are. We have a bus topology. I put a signal on the wire. Every other device connected to that main wire is going to get the signal. Collisions are going to happen because this device also wants to put voltage on the wire. What happens when you guys take two batteries and put them in series? What happens to the level of voltage, if you will? It's going to go up, right? And each time you add voltage on the wire, it's going to go up and up and up. And we won't have the ability to determine what's a 1 or what's a 0. In fact, if we're using fast Ethernet and Manchester encoding, we're going to do it with varying levels. As voltage changes from 10 volts to 12 volts to 12 volts to 15 volts, I'm going to say that's a 1. So as I'm increasing my voltage, I'm getting 1s. As I decrease my voltage, what do you think I'm going to get? I'm going to get 0s, right? I only have 1s or 0s. So as I increase voltage, I get 1, followed by another 1, followed by another 1, as I'm changing the phase, as I'm increasing. As I'm decreasing, I'm going to get 0s, which makes it really nice. The problem is, if this device is adding voltage to the wire and this device is adding voltage, then all it's going to look like is a bunch of 1s. Nothing is ever transmitted with a bunch of 1s. We're talking about binary, so we're going to have 0s and 1s. We're going to have a combination. So what's going to happen? Before this device goes to talk to any other device, it's going to do this. Sees the carrier, right? The electrical signal carrying the bits. S is the ability to sense. If there's no voltage on the wire, and by the way, there's always going to be voltage on the wire. Why is that? Interference. We're talking about copper wires. Copper wires will pick up radio frequencies. This is called the induction effect. So there's always going to be voltage. Depending on how sensitive your network interface card is, and the faster the bandwidth gets, like 1 gigabit, 10 gigabits, the more sensitive the card becomes. Hence, the distance of these technologies might be limited. This is why local area networks have a larger bandwidth, but their distance geographically is smaller. Less interference. All right, so we look at this. We know there's going to be voltage in there, but we have to have a threshold. We're going to ignore after like 5 volts. Anything under 5 volts, we're just going to ignore it. So when this thing tests the wire to see if there's voltage on there, it says, oh, it's less than 5 volts. It must be clear. If it's clear, it's going to transmit, correct? All these other devices are going to get it. Question. It's obviously going to take time for the message to go from here as well as to go to there from this device, correct? How long does it decide to wait? If it detects that there's no signal, could it just be because it hasn't gotten it yet? I mean, at this moment, I'm sending it out, and this device says, hey, there's no signal. And this all happens in milliseconds, but a millisecond may be eternity for a computer. For us, it's a blink of an eye. But a lot can be done in a millisecond when it comes to our computer power. So obviously, they both detected there was no carrier. They go to both transmit, and now we're going to have a collision. Correct? That leads to the next part. By the way, the MA after that, CSMA, carrier sense multiple access, right? Multiple access is already given to us in bus topology. That leads us to the next part, collision detection. So this is the technology that we implement when it comes to multi-access networks. We say get rid of control. On networks with smaller users, what are the chances of collisions actually occurring? Versus networks with a lot of users. The more users you have, the greater chance of collisions, correct? Seems to make a lot of sense. I mean, this is why your insurance rates are higher in the cities than they are in the country, correct? So here we are, larger areas, many users, we have to be more controlling. This is also why cities have more traffic lights than we do in the country. So fewer people. We say get rid of the controlling mechanisms. Why? Because controlling mechanisms slow us down because they add all this overhead. Does it affect performance? That depends on the number of users. You're doing this balancing act. The more control you have, the more overhead's going to be there, the more users you better have. Otherwise, you're going to be sacrificing performance. So the deciding factor to implement this deterministic approach versus non-deterministic really depends on the number of users. In fact, remind me, what was the definition of a local area network? How do we define a local area network? There's 3 conditions. Geographical location, or the size, or the number of users, if you will. The purpose, and then it's being managed by by a single organization or by administrator. Does that make sense, guys? These networks are usually implemented, these topologies are usually implemented in a local area network. So now we're dealing with the collision detection. Who's going to detect the collision? If this goes out, remember the frequency is also going out this way, and it's also going up here, and it's going to carry all the way out to the end. Who's going to detect it? How do we know a collision has occurred? We don't deal with anything acknowledgement yet. That's the transport layer. All we're doing is frames. And all my interface cards are getting these signals, and they're jotting down 1s and 0s. They're all jotting this down. So the question becomes is, how does the computer know that there's a collision occurring? When they get all these 0s and 1s that aren't adding up to anything, And then you have this increased, unridiculous amount of voltage going on because, remember, a collision occurs when two or more devices are talking at the same time, right? We add voltage. What happens when you add voltage? It's going to increase because your normal operating range for frequency should be like between 5 and 12 volts, depending on the type of mediums. I'm just giving you guys a hypothetical. So if they're operating between 5 and 12 volts, anything beyond the 12-volt range must be a collision. Who gets to detect that? Who's responsible for detecting that? Any device that first detects it will be the one responsible for a collision detection. How does it inform everybody else that there was a collision that occurred? It sends out a jamming signal to everybody. The jamming signal is going to be the highest voltage possibly imagined. And it's basically you telling your brother and sister that you're not listening to them anymore by closing your ears and doing what after you do that? Yeah, exactly. So you guys did that too, right? I'm not listening. What are you doing to the airwaves? You're jamming them up so they can't talk. So they're all going to get that. And then they're going to reset their timer. We're going to call this the back-off timer because it'll be like, okay, wait a minute. Let's let this clear again. And everybody's going to have a random timer. And then they're going to go back and recheck it. Different intervals, correct? The person with the lowest random timer is going to be the first one to transmit, if they have something to transmit. You clear about that? So this one might be the first one with the lowest timer, but has nothing to transmit. So what happens to the pathway? It's clear, correct? There's no signals. This might be the second person. It has nothing to transmit. So now we're back to us. We do have something to transmit. Before we actually go and do that, we're going to check again to see if the signal is available. If it is, we put it on there, and away it goes. This whole concept of back-off timers, jamming signals, are all involved in the Ethernet standard. The important thing is when you have a collision, it really screws things up. It affects performance because now you have to retransmit. But not only do you have to retransmit, but you have to wait, and you're idling, and nothing's occurring on your network. So what can we do to try to avoid that altogether? We implement a point-to-point network. So this is a topology called PPP. It's like me having a conversation with you. Do I have to worry about anybody else interrupting me if it's just the two of us in this classroom and the doors are shut? No. Think about this conversation. If I'm talking, what are you going to be doing? All right. We spoke about this on Monday's class, and that is we call this half duplex. Right? I gave you my driveway as an example. It's only wide enough to fit one car down through it, so if another person comes in the opposite direction, they won't be able to leave. But we can overcome this because it always depends on the type of medium we have. If I add one pair in there, then I'm just going to have the ability to do half duplex. But if I add two pairs in there, then I'll have the ability to do what? That means I can talk while I'm listening. Correct? Will I have any collisions to worry about? Hence, the media access control methods are negated. I don't have to worry about instituting control or dealing with CSMA/CD. Right? Yes, Michael. Carrier sense, multiple access. The CD at the end of it stands for collision detection. That's where that jamming signal comes in and the back-off timers are available. Whereas in point-to-point, I eliminate that concept. Now here I'm showing you guys a physical point-to-point connection. And it only makes sense. It's one node connected to another node. When do we typically see this? When did you guys ever see me draw that little Z? Yeah, wide area networks, we're connecting routers together, correct? And that's critical because most of the time we're accessing the internet. Not only am I accessing the internet, but another device is accessing the internet as well, or another network outside of my local area network. So this is going to concentrate into our gateway, correct? So there should be theoretically a lot of traffic amongst these routers. And what do we want to try to do? Minimize the chances of collisions. Now, can we take this concept and join it with this concept? And this is what we're going to call a hybrid or a star topology. I want multi-access. Why do I want multi-access? Because it allows me to scale my networks real easily. I come into it, I plug in a device, away I go. In a point-to-point network, I can't do that. In fact, remember we had to turn off our routers, add a special interface card like a serial connection, and boot them back up? I don't want to have to do that for every time I add a device on my network. In fact, that was one of the biggest issues about multi-access topologies. I have to shut down the network if I want to add a new device on it, because I'm going to literally cut this coax, add a T to it, because in order for me to use this network, I have terminators at the end of it. If I don't have these terminators, then the signal will bleed off and won't propagate back. Therefore, all my mechanisms will fail. So in order for me to add a new device on this network, I've got to shut it down, and I have to tap into the coax, the main feed, to hook up another device to the network. And in a busy network, like Wall Street, or where time is money, you can't shut down a network. The other problem with this network is if there was a crack, even right there, I might have problems with it. And it becomes hard to diagnose, hard to troubleshoot. So I want the flexibility of being able to add many users to it with the benefit of negating or minimizing the ability of collisions. And last time I showed you something called a star. A star topology obviously is going to look something like this, with nodes on the outside. But what's going to be in the center? And you'll be able to remember this because of the letter S in star. A switch is going to be an intermediary device. You see how the intermediary device is really affecting the behavior of your logical topology? Between each of these nodes and the switch, I have a private connection, a point-to-point network. We call it point-to-point protocol. This is the logical point-to-point, okay? Because in essence, it's a multi-access. Because any of these devices can communicate at the same time, undeterministic, without knowing it. So it will require that we use CSMA/CD. However, if each of these nodes are having a private conversation with the port of the switch, when they go to check their wire, it should be clean. The carrier should be available. Why? Because the switch acts like a buffer. Each port has its own memory. So when you transmit to your router, in order to get to your router, you must use your switch. To prevent collisions, what must the switch understand? To prevent collisions, what must the switch understand? What did the hub not understand? Remember, a hub would give us this type of network. What did the hub not understand? And more importantly, what do we use to make up those MAC tables or those ARP tables? The frame address, yes. Since the hub doesn't understand frame addresses, they can't identify you. That's like going to an English class where they don't know your name and they just address you guys as everybody, right? You'd have a better experience if they know you by your name than if they did by a number, correct? Likewise, here, the hub did not know you by your physical name, so it said, hey, if I'm going to say it, I'm going to send it to everybody because I really don't know you and I don't care to know you. What does a switch do? It assigns or develops a MAC table. And that is, it takes every one of the physical addresses and it associates them with a port. It's a little bit different than an ARP table. We'll talk about ARPs later. Why would a switch want to do that? So they can create a logical point-to-point between the device that's communicating with creating zero collisions or minimizing collisions. So I transmit my message. My message is stored in a buffer area. The switch looks at the frame address and says, oh, it's destined to go out here. Once that port becomes available, I will pipe it in there. So you see that you have 100% bandwidth between here and there. No collisions. As long as your memory on your switch doesn't overfill. Does that make sense? The switch will say, oh, this line became available, let me send it out. So the switch is basically coordinating events so collisions don't occur. Will a collision happen on this network? When's the only time will all the devices on this type of topology will receive a frame at once? When it's doing a broadcast, right? Sorry, ARP is broadcasting. Remember how to develop your ARP, you have to broadcast that out to everybody? So that's an example of a broadcasting, or where broadcasting is using. We good about that? So we do have to implement CSMA/CD, but how often is it used to detect collisions? Very seldomly. This gives you the best of both worlds. Flexibility, because I can add a device to my network without shutting it down. Can I troubleshoot this a lot easier? Remember the steps of troubleshooting. Ping yourself, ping your IP address, ping another device on your network. If I'm having an issue, maybe I'll unplug this and plug it into another port. Maybe it's the port, maybe it's the wire. But I'm able to narrow it down just to that one segment. Do you see the difference between logical and physical topologies now? Logical is all about the behavior. It allows us to understand the media access control. What is media access control? It depends on what type of topology we are implementing. And they're basically telling us about, do we have to share the medium? If we have to share the medium, how are we going to handle collisions? Am I going to control it, adding overhead to eliminate collisions? Or am I going to be willy-nilly about it? To say anybody talk, it's not a big network, a lot of traffic isn't happening, so the chances of collisions that are going to happen are going to be very slim. Do you put a traffic light in the middle of nowhere and say, hey, everybody has to stop? Or do you say, hey, let's remove it all. Hopefully these people have common sense. If they don't happen, then great. And where I used to live is this little country between Allentown and Reading. My grandparents lived out in the country, and there was a T intersection. I always wondered this, always. Wasn't very busy. I went under a highway, and it looked like this. Whoops, yeah, it's like that. And our house was like right here, and this was a hill, if you will. Where would you put stop sign? On the perpendicular street? There wasn't any. There wasn't any stop signs at all. I went home a year ago maybe, for the holidays, and they did put a stop sign. Put it right here. Blew right through it. For 20 years, I was used to no stop sign being there. Blew right through it. Cop pulled me over. I was like, what are you talking about, stop sign? And I look back and I go, well, damn, there is one. The reason why they didn't bother with putting any stop signs originally is this is very open, very flat. You can see in all directions. And they assumed, if you will, that if you see a car here and you're here, you're going to give the right of way, right? This person here would probably have the right of way and go up. And maybe instead of putting a stop sign there, they should have probably put what? A yield? Do you see the different controlling mechanisms? And a stop sign, I actually had to stop for 4 seconds. And a yield, it was implied before. We would look, if there's nobody there, go. Now, the yield's telling me the right of way. That if the yield sign's right here, I have to give a way to that person, right? I have to yield to that person. So maybe the yield should be over there. It would only make sense. But what if I told you more cars would go that way than this way? Now does it make sense where they put the stop sign? Still doesn't make any sense why they didn't put a yield sign in there, but nevertheless, it's all about trying to control the access. Here, there's a shared medium between these two segments. I need to avoid collisions. If a collision does happen, I need to find a way to manage it. Okay? Question?
They just put it on the
Why didn't they put it where?
Why didn't they just put it on the perpendicular one?
Because there's more traffic here than over there, so they figured they put a stop sign here for the very few people that are ever bothered with it, and then these people can keep on coming their way. I mean, would you want 1 million cars to stop every 4 seconds, or would you only want 1,000 cars to stop? Yeah, hey, I know. And that's the whole idea. It's all about how you want to implement this. So let's get a sheet of paper out. I've got a little exercise for you guys to do to show you how this is all occurring. By the way, the data link layer is filled with a bunch of standards, a bunch of protocols to be able to accept all the different types of mediums out there. And that's one of the benefits by going through a modeled approach like we are right now, is that as newer technologies are being filled, like better copper, fiber optics, microwaves, I mean, that's the biggest area right now, is we're going from like 2G to 3G to 4G. You call it LTE or whatever you guys want to call it. But nevertheless, the area of technology is in wireless, and that's rapidly changing all the time. The only reason why we have to buy new phones is not because we have to install new software on it, but because the newer wireless technology requires a different antenna, correct? And an antenna is a physical device. But naturally, did we change the software about it? Did Apple, when they released their iPhone 5, develop a new operating system to handle the LTE? Now, they did an update, but it still works on the old phone, correct? The really only reason we had to buy an iPhone 5 to get to the new 4G is because of the new antenna. That was all. But the software-wise, all that high-level stuff, the IP addresses that your phones have, in fact, the only thing that makes iPhone 5 really unique is that they got rid of the analog signal. And all your phone traffic is all digital. It's all voice over IP address. It's all voice over IP. So there is no more analog voice anymore when it comes to the newer LTE phones. It's interesting.
You can't use like the same plugins that you have for
That's another thing for the fire speeds. Yeah, it's a new lightning bolt, but that's beyond the scope of this. That'd be like a hardware class. What I'm just trying to tell you is that the data link and the physical layer have to work together because the antenna is the interface that actually puts the signal on the wire, or in this case the air, and takes it off, right? But the linking between the two allows the data link layer to adapt and evolve without changing the upper layers, like layer 3, layer 4, and layer 5. So what I have for you guys is a little demonstration of how we put mediums on the, bits on the wire. So I call this data link in action. Let's see, F5. I think that's going to be a good location. And let me give you a breakdown of what's going to happen. You guys have a sheet of paper. You're going to write down what you see, but you're not going to be writing down black, white, black, white. Every time you see, I believe, a black screen, it's going to be a 0, and every time you see a white screen, it's going to be a 1. All right? Because remember, the way we transmit is using binary. So the data link layer is taking that binary stuff and prepping it up to be delivered, to be put on the medium. We good about that? Hence the word link. It's linking the two sections, software with hardware. So here we are. The data I'm going to be sending is going to be text. So basically, I'd be taking ASCII. And what is ASCII used for those that have computer essentials? Yeah, we're going to convert letters to binary, right? Text to binary. The transport layer, I'm going to be sending you guys a port address. You'll find out what that is later. What are port addresses used for? To identify the software that's being used for sending, and then the service used to receive it. We good about that? And then the network layer stamps what? IP address, right? The IP address is logical. That's the one that will change as you take your device from one network and plug it into another network. The data link layer will stamp what for it, and where is it used for? Yeah, it's going to stamp physical address. If we're using Ethernet, we call it the MAC address. It's It's 48 bits, and that's used for local delivery. What connects us together? The medium. The medium is going to be the air. Now, instead of using sound for transmission, I'm going to use light. So when the screen flashes to a blank white screen, it's going to be a 1. It's going to stay there for 5 seconds. The only reason why I'm leaving that in 5 seconds is to let you guys know that you have time to look up the screen, look down your sheet of paper, and draw a 1. Then you can look back up, right? And black is going to be 0. We good about that? This is the software. So this is me installing the drivers in your operating system up here, letting you know when you see white, put a 1. When you see a 0 or when you see black, put a 0. All right, like I said, the medium that we're using is the air. There will be CSMA/CD being implemented. In other words, if you guys whip out your own PowerPoint and start flashing me with your lights, then I'm going to be like, wait a minute, I got this going on here. Don't be screwing up anybody else. All right, so I'm going to be looking this over, making sure that the carrier is available, right? So there's no lights flipping back and forth. All right, you guys ready? So I'm going to check the medium. Nobody's flashing me, and I'm not flashing you, so the medium is available. I know you guys are thinking something else. So, all right. Now, here, and that would work too, I guess. Close, no close, 1, 0. I think it's just more appropriate that I use the black-white. All right? So, yeah. I don't know if I'm the one doing it. So, you guys ready? By now you guys should see why it's important to set a clock rate for a serial connection, because without that 5 counting down, when it goes from a white screen to a white screen, you wouldn't know. Like in this particular case, we went from black to a black. Boy, how many bits did I put in here? That's what it's like being a fiber card, yeah. But trust me, it happens a lot faster than this. You guys wouldn't have time to write down one. In fact, it happens so fast I could even detect the change in lights. So when you guys think of 1 million bits per second, that's like this flashing back and forth a million times in 1 second. That's what fast Ethernet. Okay, finally, thank you. All right, before I actually get into how to check and verify that data was intact, transmit it, how did you guys know that it began? I had to lay down some rules, but if I come next Monday with this PowerPoint and all I do is go right into the black and whites, how would you know that it began there? I mean, you started writing down, did you guys write like a 1 for the first one? And then you write a 0 for the second one? Then a 1 for the third one, then a 0 for the fourth one. Okay, do you see that pattern? I had you guys go on, off, on, off. All right, but what if I just jumped right into that? Or you came late into class and you start looking at the screen and you tell your friend, well, you don't have to tell him anything. You just came late into the program, but you know the rules, and you start writing things down. How do you know that you grab the beginning of the frame and not in the middle of the frame? Because at this point, this is all that's happening. Right? For all you know, the very first 30 minutes of this class, or the very first 50 minutes of this class was 1, 1, 1, 1, 1, 1, 1, and then all of a sudden I changed the lights. Correct? How do you know where the beginning is and where the end's at? Because that's the same thing your interface card's faced with all the time. Exactly. You see that pattern that I developed for this? This is called a preamble, or the start of the frame. I created some kind of mechanism. Now, Ethernet likes doing this because watch the tone or the beat here. Now, if you guys have seizures, you're going to be like, but nevertheless, do you see I did that at a certain rate? I went on, off, on, off, on, off. In Ethernet, I might do that 8 bytes. So 8 times 8 would be the number of times I would do that to establish the clock rate. So there wouldn't be a clock up there. And that's why when you guys configure your Ethernet interfaces for your router, you don't have to set up a clock rate because it has a preamble. But on the serial side, you guys do. Why? Because we want to take that framing stuff and try to minimize it. By reducing the overhead, I should have better performance, correct? I don't have to worry about collisions. I know that when I put something on this wire, it's going to get to the other end. When you start receiving something, that's the beginning of it. When you stop receiving something, that's the end of it. The clock rate's set to determine when you have a 1, 1, 1. Is it a 1 now? Is it a 1 now? No different than I set up the 5. So let's do this. The very end of it, you guys should have an inverse. So go to the very last 4 bits, and it should end with a 1. Then it should go with 0, then a 1, then a 0. All right, if the first 4 bits was a 1, 0, 1, 0, and we call that the start of the frame, and the last 4 bits are 0, 1, 0, 1, what do you think that's going to be called? End of frame? Okay, the bits before there, okay, so we have 4 there. I got to make sure I count these up correct. It's going to be a 0. Let's see, a 1 in the 8, sorry, 16, an 8, a 4, a 2, and a 1. So what you guys will have is the last 4 is going to be a 1, 0, 1, sorry, 0, 1, 0, 1. Those are the last 4. The next bits, 1, 2, 3, 4, 5, 6. The next 6 bits. Do you guys have that? Okay, this is called the frame check sequence. Sometimes it's written as CRC. Cyclic redundancy checking. If you were to convert that binary number into decimal, you'd get 23. Depending on the standard and what they implemented, my standard, the way I transmit it with you guys here, is I said you should have 23 ones. Anywhere to the left of the last 10 bits. So if you count up your number of ones, anywhere to the left of the last 10 bits, you should have 23 ones. That's my formula. If you did not get 23 ones, they don't have to be in a row. They're going to be scattered all over the place. You screwed up, throw away your work, and we'll have to start over again. Because this is the only way that another device that's receiving this frame determines whether or not transmission was successful. This is the only way we verify that. Do you see I did this at the very end of this? Remember, the only time in the OSI that we add a trailer is at the data link layer. And the trailer has two major important fields in it. The FCS and the EOF. Frame check sequence and the end of frame. The end of frame is designed to tell me to stop recording. Then run a CRC, or FCS, the frame checking, to see if it was approved. Now, it just tries to detect error, and it's not perfect. Because you could have made a mistake, put a 1 here, and then a 0 there, and it could have been switched, and you still had 23 ones, correct? So it doesn't correct the errors, and it's not foolproof. It just is some kind of mechanism that before you pass it up the stack, accept it or not. Is that clear? Now that the integrity of the information was verified, what do you think the interface card is going to do next? It's going to go back to the beginning of the frame. And it's going to drop off. So you guys should have these types of 1, 0s. So this should be the final answer, but you guys probably have them strung across. It's going to go back to the beginning of the frame. In fact, let me show you this in series. If you guys did this correctly, it should look like this. This part is the start of the frame, right? This part right here is the destination MAC address. Notice it's all ones. It's a broadcast address I'm sending to everybody. If this was like 10110, then only the person whose physical address matches that binary pattern would accept this. That means everybody else in this class would discard this frame. You might have got done writing all those zeros and ones and you're telling me throw it away? That's what your computers do all the time when they're in a multi-axis topology like bus. Would that happen when you're in a star topology? If there's a switch there? No, a switch would get it, would check their MAC table, match this address with it, and say go out this port. But nevertheless, the switch is recording everything that comes in that port. All right? We will finish this up on Monday, and I'll be assigning Chapter 7's assessment Monday evening. So check this weekend. Make sure you guys go over the PowerPoints, finish up data link, and I'll wrap it up with this. There'll be a lab posted. Make sure you guys check that. You guys take care, and I will see you next Monday.